Hi, I'd like to discuss two stars in a binary star system in this video. The stars in this system have masses 2.0 times 10 to the 30 kilogram and 6.0 times 10 to the 30 kilogram. They are separated by a distance of 2.0 times 10 to the 12 meters. In the problem, we're asked, part A, what's the system's rotation period in years? And then in part B, what is the speed of each star? I think this is a really good example of different concepts in Chapter 13 and in concepts from earlier in the course, particularly concepts that will be important in Exam 4 coming up on Monday and Tuesday. So let's draw this two-star system. These two stars are rotating about their center of mass, the center of mass of the system, because there's no external force on the system. We have mass 1 located at a distance r from mass 2. And if mass 2 is 6 times 10 to the 30 and mass 1 is 2 times 10 to the 30, then mass 2 is 3 times larger than mass 1. And so the center of mass is going to be located somewhere between the halfway distance and the location of mass 2. In other words, it's going to be weighted by mass 2. We need to determine where this distance is relative to each of the masses, so we can calculate the center of mass with respect to mass 1. Say we say x equals 0 at the location of mass 1, and then perform the calculation. What is x center mass? Well, x center mass is equal to mass 2 times its distance from mass 1, which is r, over the total mass of the system. And we can call this distance from mass 1 to the location of the center mass. We can call this distance r1. Now, in this example, mass 2 is is larger than mass 1 by a factor of 3 to 1. So we could put in, for mass 2, 3r, and then we can add 1 plus 3, or 4, in the denominator. So r1 is at a distance 3/4 r from the location of mass 1. Or that's the location of the center mass with respect to mass 1. And then we can see trivially that r2 is equal to the remaining distance, r over 4. So now we know what the relative distance each mass is from the location of the center mass. And then we realize that mass 1 is going to rotate around the center of mass in a circle of radius r1. And mass 2 is going to rotate in a circle around the center of mass with the radius r2. Then we ask ourselves, what is the force that's causing each of these masses to undergo this uniform circular motion? Well, it's the force of attraction that each mass exerts on the other. And that force of attraction is F sub g, and it's equal to big G times mass 1 times mass 2 over the separation distance between the two masses squared. And that results in mass 1 feeling a centripetal acceleration. Equal to v squared, v1 squared, over the radius of the circle, r1. And this, if we are interested in calculating the rotation period for this mass, we can write down that the velocity that mass 1 has tangential to the circle is equal to the distance around the circle, 2 pi r1, over the period, the time for a complete rotation. So we put this ratio in for our expression for the velocity, v1, and we square it. Let me separate this here. Okay, so if we do the algebra, we see that, do some algebra, we see that the ratio of the period over 2 pi squared is equal to r1 r squared over big G times mass 2. And we know that r1 is equal to 3/4 r, so we can rewrite this as 3/4 r cubed over GM2. And then if we solve for the period, we see that it's equal to 2 pi times the square root of 3/4 r cubed over GM2. Now, when we did this, we could have also solved for the period in terms of mass 2, because mass 2 feels the same force, F sub g, that mass 1 does. In other words, mass 2 times its velocity squared over r2 is also equal to fg. And if we repeated the procedure that we did above for mass 1, we'll get an expression for the period that, when you evaluate it, will be the same period as the one we just found for mass 2.